Good afternoon, everyone. My name is Rio Kubota. I'm the chairman, president, CEO, and founder of Kubota Vision. I'm excited to introduce you to our company and the innovative myopia management solutions we're working to bring to patients around the world. Here are the obligatory forward-looking statements. I found the company as Acusella in 2002 with one goal in mind, to preserve and restore vision for people worldwide. We're a clinical stage ophthalmology company with a diverse portfolio of drugs and devices. We went public on the Tokyo Stock Exchange in 2014 and last year rebranded our company as Kubota Vision. Despite being a relatively small company, we have a global footprint, headquartered in Tokyo and Seattle. We have R&D on 3 continents and clinical research sites around the world. We have a diverse development portfolio of small molecules, gene therapy, and medical devices. But today, I will highlight Kubota Glass, our augmented reality-based optical system designed to inhibit myopia progression. We also are developing a contact lens version of Kubota Glass, which is in an earlier stage of development. Ours is a novel approach we believe can be a real game changer in myopia management, and new approaches are needed now more than ever. The prevalence of myopia has been steadily increasing the last few decades and is expected to continue increasing unabated over the next 3 decades. Today, there are 2.6 billion people with myopia, and that's expected to exceed 5 billion by 2050. What is even more alarming is how myopia is increasing at an even faster rate. In fact, myopia has already reached epidemic proportion in much of Asia. In many countries across Asia, more than 8 out of every 10 children have myopia by the time they are 20 years old. As we all know, the risk of sight-threatening pathologies increase as myopia increases. Every diopter counts. Bulmer and Brennan demonstrated that each diopter of myopia is associated with a 67% increase in myopic maculopathy prevalence. These increased risks, coupled with the rising prevalence rate, led the Brian Holden Vision Institute project myopia will be the leading cause of permanent blindness worldwide by 2050. This is why we embarked on the development of our first of its kind approach, combining both scientific innovations and cutting-edge technology to inhibit the progression of myopia. Human and animal studies have shown that even short-term full-field myopic defocus, where the rays of light are focused in front of the retina, can produce small but significant relative reductions of axial length. We are currently investigating optimal peripheral stimulus that will be the most effective to slow myopia progression. Most myopia control devices in both spectacle design and contact lens form that utilize the peripheral myopic defocus principle rely solely on multifocal refraction-based defocus techniques, thus yielding only dioptric control of the defocused light in a designated area of the visual field. Our e-spectacle lenses and e-contact lenses use our proprietary active stimulation technology to actively project myopically defocused images onto the periphery of the retina to stimulate the reduction in myopia progression. This approach is unique in its ability to control the size, retinal location, luminance, chromaticity, duration of activation, and dioptric magnitude of the peripheral defocus stimulus to maximize control of myopia progression. For example, full annular field versus superior hemifield studies indicate that the efficacy of myopic defocus appears to vary depending on the region of the retina is stimulated. With the Kubota glass, the location of the defocused light stimulus can be programmed as desired. We have also conducted studies to optimize the magnitude of peripheral defocus, spatial content, and brightness of the defocused image. Kubota glass active stimulation also enables control of the luminosity of the peripheral defocus targets to mimic bright photopic condition in the retinal periphery and to be brighter than the central field. In one of our studies of young adults who received 1 hour of monocularly projected peripheral defocus, which was either 5, 10, or 20 times the brightness of the background, better results were obtained with the brightest luminance 20x ambient distance of the peripheral projected stimuli. This finding highlights the importance of relative brightness of the defocused light in the retinal periphery and the importance of active peripheral stimulation. The Kubota glass system consists of a self-contained battery that powers the white light-producing micro-LED array to generate the peripheral defocus stimulus. The patterned image is defocused by +4 diopters, micro lenslets, and is projected to the retinal periphery by the percentral prisms. The distance center segment contains the patient's distance refractive error correction. On the right is a representation of how the Kubota glass system defocused light stimulus would appear to the wearer with its defocus patterns superimposed over the visual field. It should be noted that test subjects report that defocused images disappear within a couple of minutes of use. Our device consists of a 15-degree diameter clear central zone containing the distance refraction. Visual performance studies determine 15 degrees as optimal for allowing normal eye movements, reading, and comprehension when the field is encompassed by the defocused periphery. Kubota glass can manage daily treatment parameters, such as the timing and duration of the defocused light stimulus, which will allow for customized and personalized treatment for myopic progression based on the individual diurnal variations. Clinical studies are ongoing to determine the optimal duration of treatment per day. A patient at risk of future myopia progression, for example, could be prescribed to use the device for 2 or 3 hours per day, corresponding to the typical cycle of diurnally fluctuating axial length theoretically. The appropriate duration, of course, will be determined upon completion of our ongoing clinical studies. The patients then wear Kubota glass for the prescribed duration while performing normal daily activities such as classroom work, watching TV, or playing video games. The Kubota glass systems would be turned off or not worn during the downward trajectory of the normal diurnal axial length curve to facilitate a natural drop in axial length each day. Longitudinal studies are now being performed on a Kubota glass prototype on a pediatric cohort to determine the long-term effectiveness and ultimately the sustainability of this myopia control technology. Thank you.